discussed was that usually there are three states of matter. Why I'm calling usually is that because as we go to the higher classes, you'll be studying the fourth state of matter, that is plasma. But up to now, we have been studying that there are three states of matter, and they are solid, liquid, and gas. And then this is a copper wire, as you can see here. And copper wire is a metal, and the metal usually at the room temperature will be in solid state. Now, our question is, will this metal that is in the solid state conduct the electricity or not? Or in other words, we're trying to figure out if this copper wire will allow the charge carrier to move through it freely or not, okay? And then if we maintain certain potential difference between these terminals of a copper wire, then what we see here is these charge carriers are freely moving through it, okay? Hence, it can conduct electricity. Now, from this simulation, we can say that solid conducts electricity, but not all of the solids, okay? There are other insulators as well. Those do not conduct electricity, but this is a conductor, okay? And then the metal, basically. So the metal is conducting electricity as it allows the charge carrier to move freely through it while a potential difference is maintained between its terminal. Similarly, now let us try to find out if the liquid conduct electricity or not, okay? So this is a liquid, this is water, as you can see here. This is water, we're pouring down water. And now, let us bring this, okay, and mention a potential difference with the help of this battery. And then one terminal of the battery is connected to this electrode, and this is negative terminal, or the lower potential, hence it is known as cathode. And another positive terminal is connected to another electrode, okay, or higher potential, and it is known as anode. Now here it's not conducting electricity because it's a pure water, and pure water is not a good conductor of electricity. But what we are doing here is that now we are mixing some ionic covalent here, okay, or salt. Now as we mix the salt, then what we see here is the electric bulb is lit up. That means this electrolytic solution is allowing the charge carriers to move through it, okay? So what are the charge carriers here? If you happen to see here, what are the charge carriers? So see here, this is sodium chloride, and from this sodium chloride, as it comes and then get mixed up with water, then it divides into two ions, okay? One is positively charged ion known as Na+, and there is negatively charged ion known as Cl-. Now here, when this electrolytic solution is now here is being provided with certain potential difference by applying by inserting two electrodes, in which one of the electrode is inserted to the or is connected to the negative terminal, and other electrode is connected to the positive terminal. Then these charge carriers known as positive ions and negative ions will conduct, okay, through this liquid, such that you can see the bulb lighting up, that is electricity is flowing through it, okay? Now here this positive ion, that is Na+, okay, will move towards the cathode, okay? So positive ion here, Na+ will move towards the cathode, hence it is known as cation. And the negative ion, that is Cl-, this one is Cl-, okay? Negative ion Cl-, if there are two electrodes connected to two terminals, then it will be moving towards the positively charged electrode, okay? That is anode, hence it is known as anion. So here this electrolytic solution is allowing the charge carriers, that is positively charged ion and negatively charged ion, to pass through it, okay? That's why we can find the electric or the bulb lighting up, that is this circuit is closed now as the charge carriers are moving. Na+ is moving towards the cathode and Cl- is moving towards the anode. Similarly, our question is, now these are the gas molecules, then as this metallic solid conductor and the electrolytic solution, will the third type of or third state of matter, that is gas, does it conduct electricity? That is our question, okay? Just like solid, and liquid here is conducting electricity, will the gas molecule conduct electricity? So for that one, we have already discussed this one. Then what we found out was that from this slide, okay, from this slide, uh, the gas molecules, okay, usually are insulators until and unless high electric potential difference is applied. So here on normal weather condition, this atmosphere, the layer of gases do not conduct electricity. But when the high potential difference is maintained during the thunderstorm or during the rainy season, then you can find out a nice display of electric discharge. That is, the layer of gases in the atmosphere are conducting electricity when a high potential difference is being applied. Okay, so so here at this normal atmospheric pressure, around 3000 volt per centimeter of potential difference is to be maintained, okay, in order to ionize the gas molecules such that these gas molecules will conduct electricity through it, or will allow the electric charge or charge carriers to move through it. Okay, so now for the study was done, and it was done in the lab. And in the lab, what they found is that if we can monitor the pressure by using pump, then this gas inside this discharge tube can conduct electricity or can allow the charge carriers to move through it, even at a voltage of 10,000 to 15,000. Okay, so here in the natural phenomena, that is in case of lightning, there was around 30,000 volt per centimeter, but here even at a voltage of 10,000 to 15,000, the electric discharge phenomena is seen, provided that the pressure here has to be 10 mm of Hg. Okay, and now we're trying to find out the experimental setup with the help of one of the video. Okay, this is the video from HSC study lab. So this experimental setup, we're trying to visualize it, okay, with the help of this video. Now here, as you can see here, this is the discharge tube. Okay, this discharge tube is of the length 50 centimeter, and it has got the diameter of 5 centimeter. Okay, in the book it has been referred that the discharge tube can be of the length 30 centimeter to 50 centimeter, and the diameter can be of the of 3 to 5 centimeter, right? So this discharge tube is made up of 50 centimeter, and the diameter is around 5 centimeter, and this is made up of glass. As you can see here, it is made up of glass. And in these two discharge tube, or in this discharge tube, there are two electrodes fitted. Okay, this is one of the electrode, and this is the second electrode. Now, what is this electrode? Okay, is it anode or cathode? Okay, so in order to find it out, let us here. So this is the voltage that is coming on the lab. Okay, and this has been connected to the induction coil. So see here, this is the induction coil, and the secondary coil of the induction coil is connected to this electrode. So see here, this is negative voltage. So our lower potential or negative voltage is connected here. Hence, this is known as cathode. And then the higher voltage will be connected here while studying the discharge mechanism. Hence, it is known as anode. Okay, so this is the experimental setup now. Now, what we'll be studying is, now with the help of this vacuum pump, we'll be evacuating the gas molecules. Now, on evacuating the gas molecules, what will be the variation in the pressure? Okay, to study this one, I got a simulation here. Now, here, suppose this is a vacuum pump, where we're just like trying to find the analogy with the simulation. Okay, and we are using the vacuum pump such that we are taking out gas molecules through this container. Now, as the gas molecules are coming out through this container, see the variation in the pressure. We can find out the pressure is decreasing, right? So see here, now it is 72, 68, 66, 64, 62, 61, okay, 60. So see here, as the gas molecules are evacuated from this container, the pressure is decreasing. And the physics behind is this one you have studied in grade 11, and that is kinetic molecular theory of gases, while you derive the pressure, right? So as the number of gas molecules bombarding the container, the wall of the container is decreasing. So what happens? The force is decreasing. So as the force is decreasing, the pressure is also decreasing. So as you evacuate the gas molecules, the number of the gas molecules bombarding on the wall of the container is decreasing. As the number is decreasing, the momentum variation is also decreasing. So as the change in momentum is decreasing, the force is also decreasing. As the force is decreasing, then the pressure is also decreasing. Okay, so this is how we can maintain the pressure here by evacuating the gas molecules through this vacuum pump. And how much pressure is inside this discharge tube is read by this pressure gauge. Okay, so the pressure gauge will read how much pressure is maintained inside this glass discharge tube. Now see here, while studying the discharge phenomena, we'll obtain this sort of behavior, okay, or this sort of display inside the gaseous discharge tube. So see here, some in some of the regions it is dark, yes, and in some of the region it is bright. There is glow in some of the region, and there is darkness in the other region. Okay, so we're trying to understand why is there darkness in some of the region and why is there glow in the other region. Okay, and for that one, I have got a simulation here. Let us discuss this simulation. So one of you unmute yourself and then tell me what I'm pointing at here. Any one of you, please hurry up. Okay, Russ.
The atom.
Do it quick. Any one of you unmute yourself and then find a, okay, atom. Okay, and what sort of or in which state is this atom? As you can see the legend over here. So see what's written over here. Read this one.
Ground state.
Hello. Okay, ground state. So this atom is in ground state, and then if see here, if the number in this atom is changed to 2, 3, 4, 5, 6, then we can say that it is in excited state. Okay, so 2, 3, 4, 5, 6 means that this atom is in excited state. Now let me fire an electron. Okay, let me fire the electron. Then what happens here? Let us see. So see here, now it has, so see here, as soon as the electron strike this atom, the number or the legend of the atom is changed. Okay, the label of the atom is changed. It has been changed to 2, 3. Okay, but here, and then it doesn't remain for longer duration of time. Okay, the atom that has been, or the label 2 will be changed, okay, within a short duration of time, and will be labeled 1. Okay, what does it mean is that when the electron comes and strike this atom, the atom in the ground state, then it will, okay, it will excite this atom to a higher state or to the excited state. But the atom in the excited state, just like 2, 4, 5, 6, cannot remain for longer duration of time. And then with a short duration of time, they again come back to the ground state. But while they are coming back to the ground state, they will release energy, and that energy is released in the form of light. So here, these are the lights. Okay, so now when this 2 or 3 is converted back into 1, you will find the energy is released in the form of light. So that's why if there is a light, then you see a glow here. Okay, so let us here. So the electrons coming and then striking the neutral gas atoms, and the gas atoms get excited. Now it doesn't remain in that excited state for longer duration of time. Ultimately, or within a fraction of a second, it has to come to the lower ground state. Okay, and while it comes to the ground state, it releases energy in the form of light. That's why we can see the glow over here. Okay, so this glow is as the excited atom comes back to the ground state, it releases energy in the form of light. Okay, and we'll be studying more about this in the third chapter, that is quantization of energy. And then here is a dark space. So how does this dark space occur? Let's just find it out. Okay, through the help of that simulation itself. Sorry, where was that? Okay, now see here. Now as I see here, the voltage applied here was 30 volt. Okay, the voltage applied between these two electrodes, inside the discharge tube where the hydrogen atom was kept was 30 volt. Now what I'm doing is, now I am decreasing the voltage. Now as I am decreasing the voltage, let us see, okay, at 6 point, now see, these electrons are coming, okay, and then hitting on this atom, but this atom is level 1, that is in the ground state, okay. It doesn't go to the it doesn't go to the excited state, because here we have applied only 6.75 volt. On applying the voltage of 6.75 volt, the electron doesn't have sufficient energy to excite this atom to higher state. So if this atom cannot be excited to the higher state, then it doesn't release energy, okay. If it doesn't release energy, then no light is visible, and if no light is visible, it will be dark. So here, now here in this dark region, the electrons that are coming will not have sufficient energy to excite the neutral gas atom to higher excited state, as a result of which there is no release of energy in the form of light, so it remains dark over here, okay. So these are two phenomena that we observe in discharge tube. One is glow, another is dark, and I think you got the concept, okay. There is glow because the electron has sufficient energy to excite the atom to higher state, as a result of which the higher excited atom will again fall down to the ground state, releasing the energy in the form of light. That's why we can see the glow here. But if the electron doesn't have sufficient kinetic energy to excite the atom to the higher excited atom, then the light won't be, or the energy won't be released in the form of light, so there will be dark region over here, okay. So, and then I think you found out how does the pressure vary, right? The pressure vary on evacuating the gas molecules, that we have already seen. Now the next thing is, while you will be studying, while you'll be seeing the discharge in this glass tube, you'll find out that the color of the discharge depends upon the nature of the gas. Okay, if there is oxygen placed inside, you'll find different color of discharge. If you place here air, you find this different color. If you place here nitrogen, you find different color. Now we are trying to find it out, what is the reason behind it with the help of the simulation itself, okay. Now what I am doing is that now I'm increasing it. I'm increasing it to 30 volt, and then I'm placing here I place only single atom. Now what I'm doing is that I am placing here multiple atoms here, okay. So here are larger number of hydrogen atoms here, and then when I fire electrons continuously, then see here, this atom has been changed to 6 by 4 3 2, that means they are converted into excited state as the electron come and strikes this ground state atom. And then while they again from 4 5 3 2 6 they return to the 1, that is to the ground state, then they are releasing energy in the form of light. Now see here, or in the form of photon. That photon we'll be studying in the second chapter, okay. What is a photon? Now you can simply understand that the light is being emitted. Now see the color of this light. See here, try to observe it, okay. The color of this light, I think you have observed once. And then here the atom or the gas present here is hydrogen, and see the light, okay. See the color of this light. Now I'm changing it into neon. Now what happens when I change into neon? Observe it. Now as I change it into neon, so what sort of color do you find here? See here, there was no yellow when it was hydrogen. Now see here, yellow color is also being radiated out, yes or no? So see here, on varying the nature of the gas molecules, the color of the light also changes, okay. So this is the phenomena that you'll observe in the discharge tube. Now, so after all these simulations, now let us start our class, okay. So today what we are going to do is, what happens, okay, what happens when this vacuum pump evacuates the gas molecules from here and the pressure gauge read 10 mm of Hg. Okay, so the function of pressure gauge is to read the pressure inside this discharge tube, and the function of vacuum pump is to monitor this pressure by releasing gas molecules, just like here. Okay, on releasing the gas molecules, what happens here? Here, so on releasing the gas molecules, the pressure also decreases. Now here the pressure is decreasing as we release the gas molecules. Okay, so this phenomena, so here it has been slowly reducing. Okay, now we'll be doing the same phenomena. Will be evacuating the gas molecules, okay, from this container, and once we'll be studying what happens when the pressure here is 10 mm of Hg. The second phenomena that we'll be observing is at 5 mm of Hg, what sort of discharge phenomena will occur here. So what we're actually doing is, through the help of vacuum pump, we are varying the pressure, and with the variation in the pressure, what sort of discharge phenomena will be observed here, that we are going to study today. Okay, now let us start. So here, what happens when we evacuate the gas molecules from here and change the pressure to 10 mm of Hg? At that scenario, what you see is this phenomena. Okay, so this is the discharge tube. The pressure inside here is 10 mm of Hg, and between these two electrodes, the voltage of around 10,000 to 15,000 is applied. Now, what happens here? Let us see here. So what you'll be saying is, so this sort of phenomena. Okay, so that phenomena was now at a pressure of 10 mm of Hg, and when a potential difference of 10,000 volt to 15,000 volt is being applied between these two electrodes, then the phenomena that we observe is these ionized gas molecules will start conducting, or will start allowing the charge carriers to move through it. So what are the charge carriers here? Okay, so as the electron, or because of this high application of potential difference, this gas, neutral gas atom will be changed into positive ion and electron. By that, what I mean to say is that the gas molecule from the neutral gas atom, electron gets ruptured, or gets splitted, such that the neutral gas molecule is converted into positively charged ion and electron. Okay, an electron being negatively charged, it moves towards the anode, and positive ion moves towards the cathode. Okay, so electron moves towards the anode, and positive ion moves towards the cathode, such that here the conduction of electricity is possible. Or by that I mean to say that the gas molecule will start allowing the charge carrier to move through it. But while the electron moves towards the anode and the positive ion moves towards the cathode, they do not do in a straight path. Okay, they move in a zigzag path. That's why we can find out irregular lines. Okay, and then not only we'll find out the irregular lines here, these phenomena will be accompanied by a cracking noise as well. So what you find here is, at a pressure of uh, at a pressure of 10 mm of Hg and the potential of 10 to 15 kilovolt, discharging phenomena occurs in the tube. That is, the gas molecules in the tube start allowing the charge carriers, that is electron and the positive ion, to move through it. And as they are doing so in a zigzag path, irregular thin lines are seen to travel from cathode plate to anode plate, known as streamers. Okay, and then sparks and cracking noise are also produced in that scenario. Okay, now that was the phenomena that we observed while the pressure here was 10 mm of Hg. Now we again start evacuating the gas molecules and then reduce the pressure to 5 mm of Hg. When the pressure is reduced to 5 mm of Hg, what sort of discharge phenomena is observed? Let us see here. Okay, so now this thin line, this broadens out. Okay, this broadens out, and then what happens? The thin lines broaden out into a luminous column, which is bright and steady. So see here, the thin line broadens out into a luminous column. It broadens out. That means it spreads. Okay, it spreads, and then it forms a luminous column which is bright and steady. The luminous column is called gaseless discharge. This luminous column is called gaseless discharge. And color of the discharge, okay, color of the discharge depends upon the nature of the gas that which we discussed just before this slide, right? How does the color of the light, okay, or the color of the discharge depends upon the nature of gas. We have already discussed here for the simulation. Yes or no? When here was neon, different color will be seen, and when here is hydrogen, different color will be seen. Okay, so the nature or the color of the discharge depends upon the nature of gas. So at 5 mm of Hg, the thin line broadens out into a luminous column, which is bright and steady. Okay, the luminous column is called gaseless discharge, and color of the discharge depends upon the nature of gas. Now, what happens again? Now, here, now the pressure here is 5 mm of Hg. Now, again, here we are evacuating the gas molecules and reducing the pressure to 2 mm of Hg. What sort of discharge phenomena we can observe? Now, let us see here. When the pressure in this discharge tube is around 2 mm of Hg, a long luminous color appears from anode to cathode. Okay, a long luminous column will appear from anode to cathode, and this long luminous column is called positive column. And color of the discharge depends on the nature of the gas. That is, it is red for air, and blue for hydrogen. So a long luminous column will start from anode to cathode at a pressure of 2 mm of Hg, and the color of this discharge depends upon the nature of the gas. It is red for air and blue for hydrogen. Okay. Now again, we have further decreased the pressure from 2 mm of Hg to 1 mm of Hg by evacuating the gas molecules through this vacuum pump. Now, by evacuating the gas molecules and making this pressure here as 1 mm of Hg read by this pressure gauge, then what sort of discharge phenomena will be observed in this discharge tube? Let us see here. Okay, at that scenario, what happens is this discharge phenomena will be seen. So this will be seen in the discharge tube when the pressure here is reduced to 1 mm of Hg and a voltage of 10,000 to 15,000 is applied between these two electrodes. This one is cathode and this one is anode. Okay, so what you can see here, we can see here a glow. And what sort of glow is here? Blue luminous glow is here. Okay, so a blue luminous glow starts at the cathode, known as negative glow. This glow name is negative glow. Okay, and then here is certain dark region here. Here you don't find any glow here. See here, you don't find any glow here, and again here you find a glow. This glow is because of positive column, and this glow is near the cathode glow, that is blue and luminous, that is known as negative glow. And here is the dark region between this negative glow and the positive column. Okay, so as we have mentioned before, why does it happen? Here in the dark region you will find the positive ionic clouds. Okay, here in the dark region we find positive ionic clouds, and then the electrons are emitted from the cathode plate. Okay, as the electrons are attracted by these positive ionic clouds and being accelerated with a voltage of 10,000 to 15,000 volt, it comes and strikes the neutral gas molecules here, neutral gas atoms. As it strikes the neutral gas atoms, it has got sufficient energy to take this neutral gas atom to excited state, but this gas atom at the excited state won't be there for a longer period of time. Within a fraction of a second, okay, or within a very short duration of time, it falls down to the ground state, releasing energy in the form of light. That's why we can see a glow here. But here what happens? Here is positive ionic cloud. As here are positive ionic clouds, the energy of the electron is reduced as they attract the electrons towards them, right? So as the energy is reduced, it cannot excite, or the electrons cannot excite the neutral gas atom to excited state. Now, if they cannot excite, then there is no any release of energy in the form of light. So this region will be dark. Now, the region between this negative column and negative glow, the region between this negative glow, that is blue luminous glow seen on the cathode, and this positive column is known as Faraday's dark space. Okay, so this one is the Faraday's dark space. So this is what you will be seeing at a pressure of 1 mm of Hg. So at a pressure of 1 mm of Hg, what happens here is the positive column detaches itself from the cathode and move towards the anode. So as you can see here, the positive column, okay, this positive column has itself detached from the cathode and it's moving towards the anode. And then a blue luminous glow appears on the cathode known as negative glow. A dark space appears between positive column and negative glow called the Faraday's dark space. Okay, here a dark space, we can see it here, and this dark space is known as Faraday's dark space. So this was when the pressure was 1 mm of Hg. Now again, what we are doing is that now from here again, we are evacuating the gas molecules with the help of discharge, with the help of vacuum pump, right? On evacuating the gas molecules, the pressure now from 1 mm of Hg will be reduced to 0.5 mm of Hg. When it is reduced to 0.5 mm of Hg, then this is the phenomena that we'll see. Okay, or if we take this one, then this is the phenomena that we'll be observing. This is the phenomena. Okay, here a little bit here, let me see. uh, okay, so what happens is that here you can see a glow here, one set of glow here. Okay, and these are positive columns, and here you can find out the another glow near the cathode. This is known as cathode glow, and this is known as negative glow. That means now the negative glow has detached from the cathode and has moved here. Okay, and another glow has started here on the cathode, that is known as cathode glow. And there is a dark region between this negative glow and the cathode glow that is known as Crookes dark space. And here is another dark space between this negative glow and the positive column known as Faraday's dark space. Okay, so see here, so what's the difference between this one and this one? Let us see here. Okay, here what you can see here is the glow, but this glow at a pressure of 0.5 mm of Hg has detached, and it has been moving towards the anode, so it reaches here. Okay, and here is another sort of glow known as the cathode glow, and in between this negative glow and the cathode glow there is a dark space known as Crookes dark space, and between this negative glow and the positive column there is another dark space known as Faraday's dark space. Okay, so this is the phenomena that we'll see. The positive column gets shortened, right? It gets contracted. The Faraday's dark space gets elongated or lengthened. The negative glow leaves the cathode and another glow appears on the cathode called cathode glow. The negative glow moves towards the anode. Okay, the negative glow will move towards the anode. The space between cathode glow and the negative glow appears dark and is called Crookes dark space. This space is Crookes dark space. Okay, so this is what is observed when a pressure is 0. And we stop at that position 0.05 mm of Hg, then what happens? So this sort of phenomena will be seen. That is, this phenomena will be observed here. Okay, so here is our cathode glow, here is our negative glow. The dark space between this cathode glow and negative glow is Crookes dark space, and the dark space between this negative glow and positive column is Faraday's dark space. Now here what you find is the positive column has been divided into alternate dark and bright bands. Okay, so this one is a glow, and again there is dark. Again, this one is a glow, that is bright region, and again there is dark. So why does it happen here? Why do we see the alternate bright and dark bands? Because the electron that is being accelerated, okay, will have sufficient energy here in the bright region to excite the atom to the higher state, but in the dark region it will lose energy and it cannot excite, so it's dark. And again it will accelerate for a certain duration of time, get sufficient energy again to excite the gas molecules to a higher excited state. That's why it's bright, and again it loses energy here. So this process of excitation, de-excitation, loss of energy, acceleration, again gain of energy, and excitation, de-excitation of the electron continues till it reaches the anode. That's why we can find out the alternate dark and bright bands known as striations. Okay, here. So this was at a pressure of 0.05 mm of Hg. Now the interesting phenomena is, now again we're evacuating the gas molecules and we're making, or we're having only few number of gas molecules to conduct the electricity through it, and the pressure gauge reads 0.01 mm of Hg. Okay, and the voltage applied here is 10,000 volt to 15,000 volt. At that scenario, we find this sort of phenomena. So here the gas molecules has been reduced to very few in number, such that the pressure here is only 0.01 mm of Hg, and the potential difference maintained between these two electrodes is 10,000 volt to 15,000 volt. At that case, what we find is all the glow, that is negative glow and cathode glow, has disappeared. Faraday's dark space also has disappeared, and there is only Crookes dark space filling the whole tube. Okay, but we can find the fluorescence on the wall. Okay, this fluorescence is the fluorescence on the wall of the tube, not inside the tube. Okay, all the glow has disappeared, and Faraday's dark space also has disappeared, and this whole region is covered by only one dark space, that is Crookes dark space. But as here is fluorescence on the wall, and then this fluorescence depends upon the nature of the glass material by which it is made of. There the scientists predicted that there has to be certain or some invisible rays. Okay, and then they were correct. These invisible rays are known as cathode rays. Why are they known as cathode rays? Because they are the rays originating from cathode and ending at anode. Okay, so these invisible rays originating from cathode and ending at anode, which is independent upon, okay, which is independent upon, or it doesn't depend upon the cathode plate and the nature of gas placed over here. Before we studied that the color depends upon the nature of gas, but here this ray is independent upon the nature of gas, as well as it is independent of this cathode plate. Okay, that sort of invisible ray is known as cathode ray. Now in upcoming lecture we shall study how J.J. Thomson discovered electron on studying the cathode ray. Okay, so today's class is over. Now we have, so Sir, you are coming late, right? So I shall take you 5 minutes more, and then only will allow you to go. In the meantime, if you have any question, you can ask me, and then you write down PPP everyone, or I shall take your attendance. Okay, but what I am giving you here is this quiz question. You finish it within 5 minutes. Okay, and then go. Okay, you came late, so you stay 5 minutes more. Okay, and you ask the teacher to teach you 5 minutes more in the other subject. Everyone, did you find out this quiz question? Did you find it out or not? Hello, someone, so one of you please unmute yourself and then tell me, did you find out the quiz question?